In this video, we're going to look at another counting technique, and we're going to see how this ties back into sets as well. So sometimes we have sets that are disjoint. Disjoint, as it implies, are not together. And in our definition, what we mean by this is that sets are considered to be disjoint that have an empty intersection. In other words, they don't overlap at all. There's nothing in their intersection, and so we could draw them as two separate non-overlapping circles. Now, in terms of sets themselves, if A and B are disjoint sets, then A intersection B is equal to the pair of empty brackets, which a lot of times we just write as this 0 with a strike through it to indicate that it's the empty set. So you can agree that these don't intersect at all, and if I were to try to list out the elements of their intersection, there wouldn't be any. It would be the empty set. Well, sometimes we want to count the number of ways something can happen, and the sets that we're dealing with are disjoint. So if I wanted to count the number of elements that are in A and the number of elements that are in B, and they don't have anything in common, then it makes sense that I could just add the size of A to the size of B. So let's just say that hypothetically we have 1, 2, and 3. We have 3 elements in there, and here we have maybe 2 different elements. Now let's add another one in there for fun. We'll say 9, and you can agree that the number of elements in A union B, right, in A or B, if I gathered all the elements and put them together in a brand new set, it would simply be the number of elements in A plus the number of elements in B, which would be 3 plus 3 equals 6. Now this is a little bit different if those sets are not disjoint, and if they're not disjoint, then you can't simply add them together because they share some elements in common. So if A and B look more like this, and let's suppose that we had 1, 2, and then in this intersection we had the elements 3 and 4, and then B had 5 and 9. Those were not shared in common with A. So you can see that A still contains the elements 1, 2, and 3. That also contains the element 4. But 3 and 4 are in common between A and B. So if I wanted to union these together, first of all, you'd see that we don't repeat elements. Sets do not list repetitions, and so we have 1, 2, 3, 4, 5, and 9. And we can see that the size of A union B, if we counted the number of elements in that, would be 1, 2, 3, 4, 5, 6. Now, if I took the size of A plus the size of B, well, that would be A contains 4 elements, B contains 4 elements, and that gives me 8. That's too big. We know it doesn't have 8 elements. We know that the union has 6 elements. So what went wrong? Well, this 4 counts the 2 that A and B have in common, as does this 4 over here. So if they're not disjoint, we actually need to subtract away what they have in common. And on first sight, that may seem like, well, we're removing elements that they have in common, but don't we need to count those? And the answer is we actually do count them. We're just counting them twice. We count them once when we look at the size of A, which is 4, and then we count them again. Notice the crosshatch where the yellow and red overlap, that's the 4 as well, but we double counted the elements 3 and 4, so we actually need to subtract those away if we're going to take this approach, and that leaves us with the size of A union B, which in this case is 6. So this is non-disjoint. So something we'll return to more in the future, but disjoint sets have this nice feature that all we have to do is add their elements together. Let's take a look at an example. Consider the word math. How many 2-letter or 3-letter words can be created from the letters in math? Well, if we think about this as a set, first of all, the entire box, or the universe, or as we refer to it in probability, the sample space consists of, in this context, set of all words out of math. Again, assuming no repetition of the letters, only using them once, can't be repeated. And then in here, we're looking for just the two-letter words, right? So maybe we have a circle in here that just captures the two-letter words. Let me refer to that set as A. Okay, so this has, for example, MA in it, has MT, it has MH, and the list kind of goes on. Now, we know that that shares nothing in common with three-letter words. I mean, maybe they share the first two letters, but they're three-letter words. So that set of three-letter words is disjoint. The sample space S contains all the possible words, one-letter, two-letter, three-letter, and four-letter words that you can form out of those. So this would contain MAT, MAH, MTH, and so on. But they're disjoint because the words in set A and the words in set B are not the same. So if I want to figure out how big A union B is, right, I want to count all of the two-letter words, count all of the three-letter words, and add them together, then I just have to take the size of A plus the size of B. So how do I do this? Well, we can do this with permutations, but just intuitively speaking, the size of A, to get two-letter words, we have to figure out the number of ways we could fill the first letter with a letter, and then there are 4 possibilities, and then there are only 3 possibilities for the second. So there are 12 different words we can form using picking only 2 letters. To get the number of 3-letter words, well, for 3 letters, there's 4 possibilities for the first, 3 possibilities for the second, 2 possibilities for the third. So we have n equals 4, and here we're only selecting 2 of them, so we could write this as the number of permutations of 4 letters, only select 2 of them. The ordering does matter. Here we could also write this as the number of permutations with 4 letters, select 3 of them, and we would still get 12 plus 24, which is equal to 36 words in total. So here we've just applied the summation rule for disjoint sets. We just have to add up the number of elements in each. Nice and simple. Well, this also applies to any number of sets. So here's just sort of a general way of writing that. If we have these sets, and I'm using subscripts here because there could be 100 sets and we're going to run out of letters of the alphabet. So A1, set A2, and set AN, if they're all disjoint, then the number of elements in their union would equal the summation of the number of elements in each. So this is a little bit harder to draw, of course, because we don't know how many sets there are, but let's pretend that we have just all of these sets, A1 through AN. None of them overlap. They're completely disjoint from one another. We actually say that they're a lot of times pairwise disjoint for all pairings. So if you consider A1 and A3, they don't ever intersect. If you compare A2 to A58, they don't intersect. And so it makes sense that we could just add up the number of elements there with the number of elements there with the number of elements there. In other words, we don't have any overlap between them. Now, if there is some overlap, things can get pretty complex pretty fast. And so we're not going to go there with that at this moment. So here's an example of one where we have more than 2 disjoint sets. Suppose we have a programming language that allows variable names to be 1, 2, or 3 letters in length. Only lowercase letters can be used, and the digits 0 through 9 can be used anywhere except in the first position of the variable name. So for example, you can't have a variable named 1, but you can have a variable named A1, lowercase. You could have A11, for example. You could have B2C. There's just many possibilities. But we want to know the number of variable names we can create that are 1, 2, or 3 letters in length. Okay, so in this case, the sample space is the set of all variable names. And in this case, there are only variables that could be 1, 2, or 3 letters in length, and we want to know the total number of variables we can create. So I'm going to do something differently here. Instead of drawing 3 disjoint circles, I'm actually just going to split this set up into 3 portions because there's nothing outside of these. These 3 possibilities comprise all of the variables we can create. They comprise all of set S. So these would be the 1-letter words, this subset here. It's not a circle, but it's still a set within S. We could have 2-letter words, and we could have 3-letter words. I think most people think that because you're dealing with Venn diagrams, they have to be circles inside. They do not. Circles are just kind of a common thing that we do, but in this case it just makes visual sense to break it up like this. So here we would have, for 1-letter words, we could have A, we could have all the way up to Z, right? Can't have a number in a 1-letter word because you can't start a variable name with a number. 2-letter words would be like A1, A2, all the way up to, A0, A1, all the way up to A9, and then you could have, B1, B2, etc. For 3 letters, you could have something like A0, A1, and again, there are lots of possibilities there, too many to list. So if I think about this as maybe set, you call it A, B, and C if you want, since there are only 3 of them, then the size of the union, right? We want to know how many there are in total. So tell me how many there are for 1 letter, for 2 letter, for 3 letter. Add them all together because I want to know the total number of variables I can create. So it's going to be the size of A plus the size of B plus the size of C. They're disjoint. There's no 1-letter word that is also a 3-letter word. So how many 1-letter words are there? Well, there's only 1 letter, and it has to be a letter, and there are 26 possibilities since there are 26 letters in the English alphabet. But now for 2-letter words, I have 2 positions. The first position can only be one of the 26 letters. But now for the second position, remember it could be another letter, or it could be another number. It could be a number, and so there are 10 digits, and there are 26 lowercase letters. So there's actually 36 possibilities for the second position in that variable name. Similar concept for 3-letter words. I can have 26 possibilities, only one of the 26 letters. I could have a letter or a digit as the second variable, and I could have a letter or a third digit for that third component. Now notice here that we are not told that we can't repeat. Like we could have A as a variable name. There's nothing wrong with that. It doesn't say anything about not being able to repeat variable names. So in this case, using permutations is not something that we want to be able to do because we are allowed repetition, and that already violates what permutations are for. So in any case, we're still using a counting rule, in this case a multiplication principle, and I can just compute what this comes out to. 26 plus 26 times 36 plus 26 times, well, I could say 36 squared. And there are 34,658 possible variable names that you can create. And so at first, when we look at this, we might think, well, this programming language doesn't have very many variables you could create, but in any one program, you could have almost 35,000 different variables that you can create. So it's actually quite comprehensive. A lot of modern programming languages, of course, don't have any, have negligible limitations on how long variables can be, but we wanted to keep this somewhat simple. So this is all about summation rule for disjoint sets. If the sets are not disjoint, we need to evaluate that. Then we have to think more in terms of, we can't just add them together because if sets do overlap, then we might be double counting components.